You know, like all numbers, the number 2025 is a bit odd. Well, maybe that's not a great word to use. 2025 is odd, but not all numbers are odd. 4, for example, is even. But what I mean is that it's an unusual number. It's a quirky character. And since the year we live in is now 2025, this makes a prime topic of discussion. Maybe that's not a great word to use either, because 2025 is in fact not a prime number. A prime number can only be factored into one and itself, but 2025, for example, can be factored into 5 times 405, so it's not prime. But I'd like to talk about some things that are true about 2025 that you might find a bit interesting. This video has chapters, you can skip around the amusing topics as you please. Perhaps the most obvious fun fact about 2025 is that it is a square number. 45 squared, this equals 45 times 45, if you remember what a square number is, and this happens to be 2025. Indeed, it is unusual for a year to be a perfect square. Most of us have never even lived in such a year, since the previous perfect square year was the year 1936, which is 44 squared. That was 89 years ago. In fact, 89 years ago in 1936, famous mathematician Robert Langlands was born. The fact that 2025 is a perfect square year gets even cuter when you realize that we can write 45 as 20 plus 25. So 2025 is equal to 20 plus 25 squared. That's pretty funny. And there's no doubt that some of us alive today will live to see the next perfect square year. 46 squared gives us the next one, which is 2116. That is 91 years from now. So most of us won't see it, but some of us will. I will probably not be among them, for I have aged too much. By the way, a 2-digit number that ends in 5, like 45, is really easy to square in your head. Here's the trick. Imagine rounding 45 down to 40 and up to 50, and you want to multiply those together and then just add 5 squared. This is really easy to do. 4 times 5 is 20, append 2 extra zeros, that's 2000, add 25, and you can square it in your head no problem, it's 2025. There's another amusing square-related property about 2025, which is that if we add 1 to all of its digits, we actually get another perfect square number. Indeed, the number 3136 is a perfect square. It's equal to 56 squared. And well, at this point, the fun is going, and going at full force. The fun does not stop there. For if we increase only the first digit of 2025, we again get a square number. The number 3025 is square. And you may know exactly what number squared produces this based on that trick we just discussed. We would need the 2-digit number to end in 5 so that the square ends in 25, and we would need those two numbers there to multiply to 30. So it must be the square then of 55. You can imagine rounding 55 down to 50 and rounding it up to 60, giving us 50 times 60, and then just add that 5 squared, and that produces 3025. And if you would, please forget that I ever wrote a 5 like that. My first New Year's resolution is to stop waiting for a year to pass to fix the catastrophes which I unleash upon this hapless earth, but my second New Year's resolution is to start writing my 5s better. There was, in the past, a great flute player named Augustus de Morgan. He was also well known as a mathematician and logician. In the year 1864, de Morgan noted the cute fact that he was X years old in the year X squared. Of course, we've already established that a perfect X squared year is indeed a rare thing. We're not going to see another one for nearly another century. But to be X years old in the year X squared, that is indeed something very special. Augustus de Morgan was in fact 43 in the year 1849. And of course, 43 squared is 1849. So for somebody this year in 2025 to be able to say this same thing, they will need to be 45 this year. Thus, people born in 1980, rejoice. This is your time. No matter what becomes of everybody born in 1980, you will, after your birthday this year, always be able to say this special thing. I was X years old in year X squared, and for that, you have my eternal envy. Another fun fact about 2025 concerns cubes. We've talked about squares, but you may remember that a number cubed, like 2 cubed, that's 2 times 2 times 2. So we have 3 factors of 2. This happens to equal 8. And we can construct 2025 by just adding consecutive cubes. In particular, if we take 1 cubed, add 2 cubed, add 3 cubed, and so on, all the way up to 9 cubed, that actually equals 2025. So the sum of the first 9 cubes is 2025. What are the odds of that? Well, it turns out the odds were 100%. Another interesting fact is that if we add those first 9 numbers, 1 plus 2 plus 3 all the way up through 9, so we're not cubing them, we're just adding them together. If we take that sum and then square that, we again get 2025. While this may seem a little spooky, it's really more like a single fun fact than 2 fun facts. Anytime we have a consecutive sum of cubes like this, it's always equal to the square of the consecutive sum of the numbers. If you're familiar with sigma notation, we could write that fact like this. If we add up the first m perfect cubes, that's the same as squaring the sum of the first m numbers. Well, it's easy to say that this green equation is maybe not so interesting because it was guaranteed to follow from the blue equation as a result of this identity. We can actually relate the green equation to something you're familiar with. While you are no doubt familiar with many things, such as apples and roast beef on a hard roll, pretty much everybody is familiar with the 9x9 multiplication table. In the leftmost column and topmost row, of course, we have numbers that get multiplied together, and then underneath those we have all of the resulting products. There are a whole lot of numbers here in the 9x9 multiplication table, but if you add them all up, you get 2025. And that seems pretty cool, but again, it is just a rephrasing of this fact, that 1 plus 2 plus 3 up through 9 squared is 2025. That's because if you imagine adding all of these numbers in the table together, first we would have 1 plus 2 plus 3 plus 4 plus 5 all the way up through 9. The next row is that same exact thing, but multiplied by 2. So that means we have 1 copy of that sum from the first row, plus 2 copies of that sum from the second row, plus 3 copies of that sum from the third row, and so on. In total, we would have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 copies of 1 plus 2 plus 3 plus 4 up through 9. In other words, we have this thing squared, which is 2025. On a Reddit thread about interesting facts about 2025, intrepid Redditor Dr. Necro noted several amusing facts about factorizations of 2025. We previously mentioned prime numbers. Well, it's a well-known fact that every integer greater than 1 can be uniquely factored into prime numbers. 2025, as it turns out, has, as its prime factorization, 3 to the power of 4 times 5 to the power of 2. 3 and 5 are prime numbers. Those are the only 2 prime factors of 2025, and this is how they make up the number. What makes this a slightly amusing prime factorization is that it uses each of the digits 2 through 5 exactly once. 2, 3, 4, 5. That's pretty cute. We could of course also throw in a multiplication by 1 if we like. We're no longer looking at a prime factorization, but now we're factoring 2025 into consecutive integers 1 through 5. Isn't that nice? 1, 2, 3, 4, 5. Wow, that's cool. In fact, since raising 1 to the power of 0 doesn't change it, we could also write it like this. And now we've got 2025 factored in a way that uses every digit 0 through 5 exactly once. But because taking a non-zero number to the power of 0 is 1, and taking 1 to any power is also 1, we can take this further still. If we so please, which we certainly do, we can write 2025 as 1 to the power of 6 times 3 to the power of 4 times 5 to the power of 2 times 7 to the power of 0. This uses all digits 0 through 7 exactly once, where the bases are the odd numbers from 1 through 7, and the exponents are the even numbers descending from 6 through 0. Look at that. With the bases, we're counting the odds, 1, 3, 5, 7, and then with the exponents, we're counting down the evens, 6, 4, 2, 0. So this is 2025. What was the previous year that could be written in this way? Well, that would have been 1 to the power 4 times 3 to the power of 2 times 5 to the power of 0, which is that classic year 9. And of course, the next year that could be expressed in this form is the year 1 to the power of 8 times 3 to the power of 6 times 5 to the power of 4 times 7 to the power of 2 times 8 to the power of 0. This is a year I was hoping to see, though I don't think I will be able to, for it is the year 22,325,625. So clearly, we've got to appreciate this year, because a year like this does not come around very often. Indeed, the only people alive today who have ever seen such a year are over 2,000 years old. Oh, here's a good one. You're going to love this one. Imagine a number that's constructed by writing each number 1 through 45, that number amount of times. So by that, I mean I have one digit of 1, and then the next number is 2, so I'm going to have 2 digits of 2. The next number is 3, so I'm going to have 3 digits of 3, and so on. Eventually, I'd get to 13, for example, and I would have 13 copies of 13. I'm going to continue constructing this number until eventually we would get to 45, and we would write 45 times to construct this number, and, we would end with some more 45s. So that's the 43rd, 44th, and 45th 45 at the very end of this massive number. How many digits does this number have? Well, it goes all the way up to 45, and lo and behold, the total number of digits is actually 45 squared, or as we know, 2025 digits. And in fact, no other number greater than 1 has this interesting property. If we continue this and wrote 46 times, the total number of digits here would not be 46 squared. Let me convince you quickly that this number does indeed have 2025 digits. It's fairly straightforward to count. First, of course, we would have 1 digit of 1, we would have 2 digits of 2, 3 digits of 3, and so on all the way up to 9 digits of 9. Then every other number that we use in constructing this thing is a 2-digit number, like 10, 11, 12, and so on. So we would, of course, have 10 copies of 10, each of which would contribute 2 digits, so we would have 2 times 10. But then we would have 11 copies of 11, each of which would contribute 2 digits, so we'd also multiply 11 by 2 as we count up these digits. Then we would have 12 copies of 12, and each of those would contribute 2 digits, so 2 times 12, and so on all the way up to 45 copies of 45, each of those again would contribute 2 digits. Now this is a lot of addition, but thankfully there are well-known formulas to make this easy to calculate. First, the sum of 9 consecutive integers from 1 through 9, that is just the last number, that's 9, times the next number, which is 10, divided by 2. Then we have 2 times all of this stuff in parentheses. Again, this is a sum of consecutive integers, 10 through 45. Although it doesn't start at 1, there is still a simple way to calculate the sum. So we will have 2 times this sum. How do we calculate it? Well, we have to take the total number of numbers in the sum and divide that by 2. How many numbers are in the sum? Well, 10 through 45, that's a total of 36 numbers. So we have 36 over 2. And then we just have to multiply this by the first number plus the last number. So 10 plus 45. Then we'll run the numbers on this. This is 10 over 2 is 5 times 9 is 45. And then for this over here, 2 over 2 cancels out. 10 plus 45 is 55. And then multiply that by 36. That gives us 1,980. And indeed, this adds up to 2025. We have one more 2025 fun fact to discuss, which concerns graphs. In the mathematical field of graph theory, we study things called graphs, which are structures consisting of vertices and edges that join pairs of vertices. This is an example of a graph, and this is called a cycle. Hopefully you can see at a glance why it would be called a cycle. Another example of a cycle graph is seen here, and an example of a graph which is not a cycle is seen here. This graph is in fact an example of what's called a tree graph. That's because it's connected, which means we can get from any vertex in the graph to any other by traveling along the edges. So it is connected, and it contains no cycles. It doesn't contain any shape like that or that. There are no cycles in this graph. So it's connected, it has no cycles, it's a tree. If we put an edge right here joining those two vertices, there would then be a cycle, and it would no longer be a tree. There's also a thing called a subgraph, which is exactly what it sounds like. For example, I could take some vertices and their adjoining edges from this graph to get a subgraph. I could take those two vertices and the edge joining them, and hey look, that is a subgraph. It's just part of this graph, but I could look at it on its own as its own graph if I wanted to. If we labeled the vertices of the original graph 1, 2, and 3, then this subgraph I've taken only contains the vertices 1 and 2, so it's not what we would call a spanning subgraph. A spanning subgraph doesn't have to contain all the edges, but it does need to contain all the vertices. Of course, if we wanted to, we could include the vertex 3 and this edge that joins 2 to 3. I have to kind of squish it in here, but let's say we included that vertex 3 and that edge joining it to 2. Now this would be a spanning subgraph, because it does contain all the vertices of the original one. And notice this spanning subgraph is actually a tree, because it's connected and it has no cycles. Of course, if we included that last edge, it would have a cycle, but it doesn't. So it's actually what we call a spanning tree. It's a spanning subgraph which is connected and has no cycles. One common type of question in graph theory is to figure out how many spanning trees a particular graph has. For example, another spanning tree of this graph would have all of the vertices. Again, that's required. You've got to have all the vertices in a spanning tree, 1, 2, and 3, but then maybe I take this edge that joins 1 and 3, and this one that joins 3 and 2. This is a different spanning tree. In total, it's easy to see that this graph in fact has 3 spanning trees, because each spanning tree has to omit one of these 3 edges, which gives us 3 options. Now, what does this have to do with the year 2025? Well, bear with me, okay? We are getting there. Here, I am drawing for you another graph. In particular, this is an example of what's called a complete bipartite graph. It's bipartite because we can separate the vertices into a red set and a blue set so that no vertices of the same color have an edge joining them. So it's bipartite. It's split into these 2 parts, in this case red and blue. None of the red vertices have an edge between them, and none of the blue vertices have an edge between them. It's a complete bipartite graph because it has every edge it can possibly have for a bipartite graph. None of the blue vertices have edges joining them, but every blue vertex and every red vertex is joined by an edge. This particular complete bipartite graph would be denoted K, 2, 3. It's a complete bipartite graph with 2 vertices in the first set and 3 vertices in the second set. Of course, one may consider asking how many spanning trees this complete bipartite graph has. Just as an example, I could highlight the edges that we might include in a particular spanning tree. Remember that a spanning tree has to have all the vertices, but that would just be an example of the edges such a spanning tree could have. And if you run the numbers, it actually turns out this complete bipartite graph has 12 total spanning trees. Now, I want to consider a more general problem, which is how many spanning trees does a complete bipartite graph have if it has a set of 3 vertices and a set of, we'll say, n vertices. So one set is fixed with 3 vertices, but the other set can have any positive integer number of vertices. And we're writing s of this to denote the number number of spanning trees the complete bipartite graph has. So how many spanning trees could such a complete bipartite graph have? Well, let's draw some diagrams and crack this case. So we know that one of the sets of vertices has to have 3 vertices. We'll say that's the red set and call those vertices A, B, and C. For the sake of this argument, we'll suppose that the other set of blue vertices has at least 3. In this diagram, I've just written 4. It could be any number. We'll suppose it's at least 3. The smaller cases are very easy to address, so I'm not going to bother mentioning them. Now remember, we're considering spanning trees, and in a spanning tree, it needs to be possible to travel between any pair of vertices. In particular, it needs to be possible to travel from A to B, and from A to C, and from B to C. Now, one way that might happen in a spanning tree is that the distance between all of these pairs of vertices is 2. That could happen if one particular vertex in the blue set has an edge joining it to all of those vertices in the red set. That's a possibility. We'll call that vertex X. So in this case, the distance between A and B is 2, the distance between A and C is 2, and the distance between B and C is 2. And now it's pretty easy to count the total number of spanning trees that have this structure. There are, let's say, n total vertices in the blue set, right? That's this number here, n vertices. Thus, there are n vertices we could choose to be this guy X that has an edge joining it to all of the red vertices. So we have n choices for X, and then for all of the other n-1 vertices, every other vertex other than X in the blue set, they all have 3 options. Each of them could be adjacent to A, so there's an edge joining it to A, or there could be an edge joining it to B, or an edge joining it to C. No other vertex can have an edge joining it to 2 of the red vertices, because if that happened, we would then have a cycle, which isn't allowed in a spanning tree. So all of those other n-1 vertices, they have 3 choices. Have an edge going to A, to B, or to C. Hence, to count the total number of spanning trees with this structure, we would multiply by 3 to the power of n-1. That is 3 choices for all of those n-1 other vertices. So that's counting all of the spanning trees that have this particular setup, but there is one other possibility. The one other possibility is that a pair of red vertices has distance 2, like A and B, and another pair of red vertices has distance 2, like B and C, but then the other pair, namely A and C in this case, has a distance of 4. There's no way for the distance between 2 red vertices to be greater than 4, because remember, this is a bipartite graph, so every edge would take us from the red vertices to the orange vertices, back to the red, back to the orange, and back to the red. And there's just not enough red vertices to go back and forth enough times to get a distance that's bigger than 4. So this is the only other possibility, and just as in the previous case, the other orange vertices, which I haven't drawn edges on, can have an edge going to exactly 1 red vertex, otherwise a cycle would be created. So how many spanning trees are there like this? Well, there are n orange vertices, and we need to pick 2 of them to play the role of y and z. That is easily counted. It's a binomial coefficient written like this: n choose 2. It's the number of ways we can pick 2 vertices from a collection of n vertices. I'll leave a link in the description to my video going over this if you've never seen it before. So that counts the number of ways we could pick y and z, but then there are 3 choices for which red vertex would play the role of B. A could be in that spot, B could be in this spot, or C could be in that spot. So that gives us an additional 3 choices. But then, whatever red vertex is playing that role of the middle, we have 2 choices for the left and right side. A and C could be swapped, so that's an additional 2 choices. And then, like we said, all of the n-2 other vertices in the orange set, the n-2 vertices other than y and z, they all have 3 choices. They can have an edge going to A, or an edge going to B, or an edge going to C. Thus, we have to multiply by 3 to the power of n-2. 3 choices for n-2 vertices. Now, there is a simple formula for calculating these binomial coefficients. So n choose 2, what is that? It's n factorial divided by 2 factorial times n minus 2 factorial. And then 3 times 2, of course, is 6, and we have multiplied by 3 to the n minus 2. Then n factorial divided by n minus 2 factorial, that's just n times n minus 1. 2 factorial is 2, and 6 divided by 2 is 3. Thus, we don't have n minus 2 copies of 3, we actually have n minus 2 plus 1 copies of 3, which is just n minus 1 copies of 3. So to count the total number of spanning trees of the complete bipartite graph K3n, we have to take this and add it to that. And what we have here is 1 copy of n times 3 to the n minus 1 plus n minus 1 copies of n times 3 to the n minus 1. In total, that's n copies of n times 3 to the n minus 1. In other words, of course, that's n squared times 3 to the n minus 1. That's the number of spanning trees of this complete bipartite graph. Finally, if we look at the number of spanning trees of the complete bipartite graph with 3 red vertices and 5 blue vertices using our newly discovered formula, what do we get? Well, we get n, which in this case is 5, squared, multiplied by 3 to the power of 5 minus 1. That's 3 to the power of 4. This, of course, is the prime factorization of 2025. So the complete bipartite graph with 3 red and 5 blue vertices has 2025 spanning trees. That's gotta mean something good about this year. So those are some fun facts about 2025. I hope you got a kick out of it, and please do let me know in the comments if you have any questions. Be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, feeling art to keep the cable cut and untuck the table. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake cause I'm jaded. Hate the odds that I calculated. Press and pull and pray and push it all the way through the whole blue planet faded. Psychosomatic habits, why you so